Hello students, this is the Week 2 lecture on organizing, summarizing, and displaying data. We hope to answer the question, how can I display information? You can already see a couple of different choices here. You have a table, or two tables I should say. One of the tables is a frequency table. One of them is more like a relative frequency table, although these numbers don't appear to be exact relative frequency. This is a bar graph. This is a pie chart. There's just a bunch of different ways of displaying data. Once you contain and collect all of these pieces of data, how can you show them to somebody else without making their heads spin around and confusing them? All right, first let's take a look at what raw data is. The word raw data, or the term raw data, does sort of make my nose crinkle a little bit. When you think of the word raw, you should think of like, raw meat or something like that, just something that's not cooked yet. And when you think of raw data, it's data that hasn't really been prepared or organized yet. Data that's not organized, as it says, is referred to raw data. You need to be able to organize data so that people understand it. And there's a lot of different ways to do that. You can put it in a table, you can put it in a graph, or you could calculate numerical summaries. That's what we call statistics. It's a numerical summary of a sample of data. All right, moving on to the next slide here. Data tables are another way of organizing data. For example, a frequency distribution, just saying how frequently certain values come up, lists each category or class of data and the number of occurrences or frequency of each category of data. Now you might say to yourself, well, what do you think that would look like? Don't worry, I'm going to show you on the next slide. Keep in mind that a frequency distribution is organizing data into categories for comparison. Like, if I'm collecting everybody's weight in the classroom, I might group you into, the folks that are 100 to 115 pounds, and then 115 to 130, then 130 to 145, etc. I'm grouping you into categories for comparison to say, oh, I think there's way more students in this category than there is in that category. And these frequency distributions or frequency tables definitely lend themselves to using bar graphs or histograms. Specifically histograms, I'm going to show you how to transform a frequency distribution into a histogram. That's one of the big tasks that you're going to be asked to do on the final. Here's an example. We have the heights of 10 students in centimeters. And of course, this right here, let's grab a pen here. This right here is called raw data. It's raw data because all it is a list of numbers not organized in any sort of way. It's not even listed in order. It's just exactly what you collected when you walked around and asked people the question, how tall are you? Then we organize that information into a table. This is called a frequency table, also known as a frequency distribution. This tells us how often these things come up. For example, how many 139s are there in the class? There's one of them. How many 145s are there in the class? There's two of them, right? There's one 145 here, and there's another 145 right here. So it just tells you how often, how frequently the value comes up, right? And then over here, the last thing on this slide is a frequency bar graph. We know this is a bar graph and not a histogram because the bars don't touch. We'll talk about that a little later, but I think your algebra teacher probably, or 8th grade teacher probably talked to you about histograms a little bit. This is a bar graph because each bar represents the frequency, how often the value shows up. And notice that these values are organized in order in terms of smallest to largest. A frequency table does not have to be listed in order. It should be, but it doesn't have to. But a bar graph or any other graph like a histogram must be organized in numerical order, right? 136 is the smallest, 152 is the largest, and so on. All right, moving on to the next slide. In the next slide, I'm giving you a bunch of data about the color of M&Ms in a bag of plain M&Ms. Now, this video is in no way sponsored by the M&Ms company or any affiliated company. So if you are a copyright holder for M&Ms, please go ahead and just ignore this for a moment. Construct a frequency distribution of the color of plain M&Ms. Remember, a frequency distribution is just going to be a table that has all of the different colors of M&Ms. And we can see that very easily down here. This is the raw data for the M&Ms. The first one that I pulled out of the bag and ate was brown. The next one 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 was brown. How lucky. But then the next one was yellow, right? So we didn't have them organized, right? Because there's yellows, but then there's also other yellows down here. They're not organized in any sort of way. This is just raw data. What we can do now is take this data and put them into a frequency table. And the frequency table, again, frequency is just short for how often. So how many brown M&Ms came up? There were 5, 10, 11, 12. I know that sometimes students get confused by these tallies because most of the time students do tallies like this. They'll do 1, 2, 3, 4, and they'll strike out the fifth one. These tallies and these tallies are equivalent to each other. You don't have to get too crazy about it. I put these tallies because this is how a computer writes the tallies. A computer doesn't do that slash through very well. So, but anyway, the tally column is what you're looking at when you're in the process of counting and sorting the data. Once you get a complete tally, once you've emptied the bag, in this case, you can take that tally and turn it into a frequency, which is numerical data. I know that there's 12 tallies, so 12 is the frequency. I know that there's 6 tallies, 6 is the frequency, and so on. It tells us that there are twice as many brown M&Ms as there are orange M&Ms. There are 4 times as many brown M&Ms as blue M&Ms, so we can look at it comparatively. An easier way to look at these values comparatively is by turning it into some sort of bar graph or histogram. And in order to do that, we'll be talking about that a little later in the course. But let's talk about relative frequency. I know that I spoke about relative frequency at the top of the video. Relative frequency is the proportion or percent of observations within that category. In other words, if I were to say this is my absolute frequency, just frequency, my relative frequency would be this number out of how many total M&Ms there were. Well, how many total M&Ms were there? If you counted them all up, you would see that there was 45 M&Ms total. So the answer to this, the relative frequency, which sometimes we call R-freq, which is not a very nice thing to say, the relative frequency is going to be 12 divided by 45. And we convert that most often we talk about relative frequency in terms of a decimal, right? Frequency divided by the sum of all frequencies, converting to a decimal. So 12 out of 45 is just about 0.26 repeating. So I'll write it down as 0.267. I've rounded it, and depending on the question, it'll tell you what to round to. It'll generally be pretty obvious what to round it to. Okay, so that's how you calculate relative frequency. You divide whatever frequency it is for the category that you're looking at, divided by the sum of all frequencies. All right, so the relative frequency table does look like this. We found that 0.26 repeating, or 0.2667 as we round it, and all of these other values are rounded as well. See that we turn frequency into relative frequency. All right, we're also able to construct a bar graph for data like this. Remember, the bar graph is constructed by labeling each category on the horizontal or vertical axis. Almost always, we're going to be dealing with the horizontal axis for the categories. And then almost always, always in this class, almost always in life, but every time in this class, horizontal will be the categories and the frequencies will be on the vertical axis, right? So let's add that in. So you can see that the categories are on the horizontal and frequencies are on the vertical. That's how you read a bar graph. Let's take a look at what a bar graph might look like. This is a bar graph that compares the different M&M's colors. And this is a nice graphical way to show that there's a lot of brown candies in there. That number of brown candies eclipses all other candies. And it's really not even close. Like blue is down here at 3, brown is up here at 12. You can see it's like poking up a little bit, but that's just because of the width of the line here. And you can easily see that yellow is 10, red is 9. This is a nice way of encoding information into a diagram so you don't have to write it down. A picture is worth 1,000 words, right? And notice that these bars aren't touching because brown and yellow, there's no real overlap there. Yellow and red, there's no overlap. These are pieces of qualitative data. They're nominal qualitative data because it's just names. So there's no need for the bars to touch at all. They're individual categories. All right, and a relative frequency bar graph, you can see that this is relative frequency because there's decimals on the side here as opposed to actual counts, but I want you to see, this is frequency, this is relative frequency. Not a big difference, is there? Right? The only difference is the scaling on the side. The relative frequency doesn't change that there were more brown than blue, right? It doesn't change that at all. Okay, so I'm glad that you were able to see that side to side. Now let's talk about what a Pareto chart is. The Pareto chart's job is just to organize the bars in decreasing order of frequency. So this Pareto chart is often used with qualitative data like colors of M&Ms. The Pareto chart is not often used when you're dealing with numerical quantitative information, right? Because you don't want to rearrange the quantitative data in the wrong order. But with nominal qualitative data, you can reorder it to your heart's content, right? We just slid it around so that, oh, it looks like blue got cut off here. But yeah, blue is the smallest color. Blue should be over here. Okay, so that's the idea. What you're doing is changing the chart so that it goes from highest to smallest, right? It goes in decreasing order of frequency, so it starts from the highest frequency and then goes down from there. Moving on. So we're going to save the discussion questions for the actual lecture in class. But let's take a look at comparing two data sets and give you motivation as to why we construct data displays. So in this case, we have marital status of U.S. residents 18 years of age or older in 1990 and 2006. Here in 1990, there was 40.4 million people, million U.S. residents 18 years of age or older that were never married. 112.6 million residents that were married. And then in 2006, those numbers changed. There are 55.3 million people that never married, 127.7 million people that were married, and so on. It's hard to compare these two groups, however, because we're not really comparing apples to apples. First of all, there were more people in 2006 than there were in 1990. So what we're going to do is draw a side-by-side relative frequency bar graph. Relative meaning we're taking each of these values and dividing by the total in the column. Notice that since there's way fewer people in the 1990 column than the 2006 column, it may be that even though this number is smaller than this number, it might turn out that the percentage of people that were never married is close to the percentage of people that were never married from 1990 and 2006 respectively. So, side-by-side relative frequency bar graph, here's what it looks like. If you can take a look at this bar graph, it tells us now side by side because the blue and the light blue and the dark blue are right next to each other, right? Light blue, dark blue, and the light blue represents 1990 and the dark blue represents 2006. So despite the fact that these numbers on the previous slide did look pretty significantly different, right? The 40.4 versus the 55.3, the 112.6 and 127.7 looked like they were pretty significantly different. They're not really, right? These values are pretty close to each other, right? And it also looks like these went up, but these went down. These went down and these went up, right? You're able to make those comparisons as far as which one went up and which one went down and whether they're very different or not just by looking at the relative frequency bar graph. Okay, take a look at interpreting bar graphs. Oh wait, this is an example. We do these in class, so let's move it along. All right, let's talk about pie charts. A pie chart is a circle divided into sectors. Now, if you took Algebra 2 already, you know that a sector is just a wedge of a circle, kind of like a slice of pizza pie. Each sector represents a category of data. So all the different sectors in a pie chart, all the different wedges are going to represent a different category, and it represents how large that category is as compared to everything else. So I'm looking at this pie chart. It is all of the folks and their marital status in 2006, similar to that diagram that we just looked at. And you can see that the majority of people, that 58% of people, were married, color-coded with red. And also the area of this wedge corresponds to how many people were married, 127.7 divided by whatever the total number here is. Now, statisticians, as you could probably have guessed, don't like pie charts. Why don't they like pie charts? Good question. To answer it, let me ask you this. What angle is it here between this side and this side? What's that angle? Well, if it was exactly 50%, that would be a 180-degree angle. If it's 58%, then, oh gosh, you have to do, x divided by 360 equals 58 over 100. And then you'd have to use a protractor to measure out the angle, and then you'd need a compass to draw. It's hard to draw. It's much easier to draw a bar graph, a histogram, a stem and leaf plot, a box and whisker diagram. It's much easier to draw those other diagrams than it is to draw a pie chart. So I can say that as a person who is a statistics enthusiast myself, pie charts are not where it's at. They're nice when you can generate them on the computer, but they're not very easy to make yourself by hand. One thing that was easy though, 25%, right? That's a right angle. So it just happened to luck out that people that were never married are 25% of the total, right? 55.3 is 25% of the total. Anywho, let's move it along here. If you were to construct a frequency distribution of raw data, here's what it might look like. These data represent the number of available cars in a household based on a random sample of 50 households. So you randomly select 50 households and you call them on the phone and say, hey, you got any cars over there? And they say, yes, as a matter of fact, I own 3 cars. Or our family owns 3 cars. Oh, no, our family doesn't own any cars. Oh, yes, our family owns 2 cars, right? 50 times that happened. And this is based on results reported by the U.S. Bureau of the Census. A great bureau, in my opinion, because they're a bunch of stat nerds like me. So a random sample of 50 households, this is all of them. This is ugly to look at, and it's hard to make any decisions. And in general, it's just not, it's not very user-friendly. So what we're going to do is take these values, these raw data, and convert them into a frequency, and then a relative frequency distribution. Let's look at those now. So what we did was we went through and we tallied up all the zeros, all the ones, all the twos, and quickest way to do that, in my opinion, the easiest way to do that is make a chart of 1, 2, 3, 4, can't skip 0, can't skip 5. I think 5 is the highest, right? And then for every one of the numbers, we cross it off and we put a tally. We cross it off and we put a tally. Cross it off, put a tally. Cross it off, put a tally. Cross it off, put another tally for 1, right? And keep on doing that until everything's crossed off. That's your procedure. You're welcome for that in advance. That's a pro tip. Anyway, so that's how you collect the tallies. The frequencies are just the tallies added up. And then the relative frequency, the R-freq, is just 4, in this case, the frequency, divided by 50. And every one of them is divided by 50 because that's the total number of things. Okay. And then again, notice the tally marks, which can also look like this. This is a tally mark by hand. These are tally marks on computer. They're slightly different. Okay, I don't want to breeze past this. This is a frequency distribution, and it is also a relative frequency distribution. It meets both criteria. So if the question asks you to make one of these things, that's how you do it. A histogram from the Greek, because as you know, all words in math are either Greek or Latin. Histogram is constructed by drawing rectangles for each class of data whose height is the frequency or relative frequency of the class. So, in other words, for each one of these categories, in this case number of cars, we are going to draw a rectangle that goes up to a certain height. So for example, the number of cars 0, the height of this rectangle would be 4. For number of cars 1, the height of this rectangle would be 13, and so on, right? We're just identifying each of the different categories and how tall the bar is based on the frequency. And that'll tell us, kind of like in a bar graph, right? That'll tell us which one of the categories is largest. Okay, moving on along here. Here's an example of a histogram for the available cars in a household. Notice that all of these bars are an appropriate height for the number of times that that number came up. Like 2 came up 20, I think it was 22 times. So this, the number of cars in the household 2, that happened 22 times, or 22 households reported that they had 2 cars. That's how you read that. One other thing that you should observe, since this is a histogram, we got no space in between these bars, people. That means that the bars are touching. They are, in a histogram, the bars touch. Here's histogram number 2. The only difference between this and histogram number 1 is that this is relative frequency, so the decimals are on the scale instead of the actual numbers of the frequency. Keep in mind that it doesn't change the shape in any way. Moving on to frequency distribution for continuous data. Okay, so it was easy to say, well, how many times did 2 come up? I'm just going to count the number of 2s. How many times did 1 come up? I'm just going to count the number of 1s. However, with continuous data, which could take any decimal or any subdivision of decimal that it wants to, it's a little bit more difficult to do. So what what's gonna take place is that every piece of data that you collect, you're gonna say this piece of data is between here and here. And then based on that, you're gonna put it into a bucket. Now this bucket is from all the numbers from 10 to 12. This bucket is all the numbers from 13 to 15. This is all the numbers from 7 to 9. Now, 12.1 is in this bucket because it's from 10 up to really all the way up until 13, right? It's 12.1, 12.2, all of the 12s are in here, you should say. And then all the 7s, all the 8s, and all the 9s are in here, even like 9.8 is going to be in this bucket, right? So this value goes in this bucket because it's one of the 9s, right? This 7.6 also goes in that bucket, as well as 8.7, because these are some of the 7s or 8s. So you're organizing these values, these pieces of raw data, into classes or buckets or intervals. All of those are appropriate. Buckets is something that you might see in like an old-timey textbook, but it's still used today. And then you convert them into tallies, just like you would do on a relative frequency table or a regular frequency table. Class intervals and widths. Now, once you have collected your data, you sort of have to determine what you're going to do in terms of class intervals and how wide you want the intervals to be. So for example, these buckets were from 1.0 up till like 3.99, right? So the class width here would be 3, right? 3.99 is essentially 4. 4 minus 1 is 3. There's 3 different, like the width of this class is 3. Same thing here. 4 to 6.999, that's essentially 4 to 7. That's a distance of 3. So the class width in this case is 3. But it didn't have to be. We just arbitrarily did that. What if I went in this bucket all the 1s and all the 2s, and in this bucket all the 3s and all the 4s? I could have chosen it that way as well. It's a little subjective to figure out what you want to do in terms of class width for your buckets. You also need to know how many how many classes you would like. For example, in this case, how many classes are there? 1, 2, 3, 4, 5. 5 classes, otherwise known as intervals, also otherwise known as buckets, right? Sometimes the problem will say, I want you to use 7 classes or 7 buckets. Sometimes it'll say, make the frequency histogram based on what you think is right. There are a couple of different rules about class intervals and widths. Rules, I know, right? Some of the rules are they're exhaustive, which means every data value has to be in a bucket. Like if in this situation, if there was a data value of 20, that would be no good. This is not exhaustive because there's nowhere to put the 20, right? There's no bucket for it. So you either have to make new buckets to keep that 20, or you have to reevaluate the way you collected your data. Let's see. Next, they have to be non-overlapping, which means you can't be able to place one value into 2 intervals. So this is 9.8. I knew without a doubt that this 9.8 goes into this bucket here, because this is the bucket for all of the 9s, right? Everything from 9.0 to 9.99, right? If I said this bucket was everything from 4 to 7, all the 4s, 5s, 6s, and 7s, then where would I put 7.6? Would I put it here or would I put it here? There can't be that ambiguity, so therefore you cannot have overlapping buckets or overlapping class intervals. Next, you must have continuous buckets. They can't skip any possible values. There's no gaps. So these are all the 1s, all the 2s, and all the 3s, all the way up to 3.9999999. As soon as you get to the next number, that's 4, you got a new bucket. It can't be just 1 through 3 and then 4 through 6 just like that, because where do I put 3.5? Does it go here, or does it go in the middle of the 2 buckets? That's not allowed. That's why we're saying that these buckets are from 1 to 3.999, from 4 to 6.999, etc. And then last but not least, they have to have equal widths. You can't have buckets with different sized widths. So this bucket has 3 values in between the lower bound and the higher bound. This has 3, this has 3, this has 3, etc. So they have to have equal widths. If they're not equal widths, then your histogram can't be drawn correctly. In other words, the width of this bar would have to be different than the width of that bar. That would look silly, and you'd never do that. You'd be thrown out of statistics land forever. You don't want to do that. Okay, so here's what the class intervals convert to when you actually talk about an inequality. Remember the bucket that was from 1 to 3? It was really from 1 to like 3.9999999. So in other words, it's all the values starting at 1 and getting up to, but not including 4, right? Starting at 1, so there's an equal sign, but getting up to, but not including 4. As soon as it hits 4, it ticks over to here, the next value, right? As soon as this hits 7, it ticks over to the next value. So there's no ambiguity as to where to put the 4, where to put the 7. If you got a value of 10.0, it wouldn't go in this interval, it would go in this interval, because that's where the tens go. There's an equal sign here. What is the class width here? Well, as we said before, the class width is going to be everything from this value, the 4, to this value, the 1. So it looks like the class width here is 3. Moving right along. Class intervals and widths. You can see that these classes are the classes that we just talked about here, written as inequalities. And we wrote down all the tallies, put down the frequencies, and found the relative frequencies by dividing each frequency by the total number, which is 2, 3, 6, 8, 9. Right? Dividing everything by 9. All right. Here are some tips for frequency distributions that you need to know. One of the best tips that I can give you is that you're supposed to use, or you should use, between 6 and 12 classes. Usually somewhere right in the middle there, maybe 8 or 9 classes is the sweet spot. Because if you use too many classes, it's going to be hard to see the shape, right? Here's an example. 1, 2, 3, 4, 5, 6, 7 different classes. This has no values in it, but we can still see the pattern here. It like kind of goes up and down. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different classes, and it's all over the place. It's all jagged, so it's hard to tell what the pattern is. My suggestion to you, try to use between 6 and 12 classes when you're setting it up yourself. All right, moving on to other data displays, we'll buzz through these. A stem and leaf plot, also known as just a stem plot. That's not just an evil plan to get your science and math teachers together to, to rule the world. A stem plot is taking all of the digits in your raw data, separating them into usually first number and last number, making the first number the stem and the second number the leaf, right? Keep in mind, if you're doing this, if you're going to do this procedure, every number in between the smallest stem and the largest stem has to be included, even if there's no values there. So for example, in this case, if we didn't have 30 and 32, we would still have to put a 3 here. We would just leave it blank. Just like here in the previous example of the histograms, there was nothing in between 680 and 690. We had to have it on the graph anyway. Okay, and this is how to place 32, 32. And this 0 represents 30, 30. Let's see. Other data displays, stem and leaf plots. An easy way to turn this into a stem and leaf plot is say, well, all of the whole numbers is going to be my stems. All of the decimal parts is going to be my leaves. So here is an example of that. And we've just taken this raw data right here, and we've baked it up into a lovely stem and leaf plot. And you can see like there's a shape to it. There's a pattern to it. It's easy to see once you make that stem and leaf plot. A couple of steps in making the stem and leaf plot. They're very self-explanatory. If you need these copied down into your notes, go ahead and pause the video and take these down. Not necessary really for me to go over. It's just here's what you got to do to make a stem and leaf plot. All right, there's another data display called a dot plot. And a dot plot is really useful because it doesn't really require any very sophisticated drawing technology like a compass or a protractor or anything like that. You draw a straight line, you mark it at regular intervals, and then you mark down dots for all of your pieces of information or all of your data. Here's that car data for the 50 households. If I was to draw a dot plot, all I'd have to do is draw a straight line, a straight horizontal line, mark off 0, 1, 2, 3, 4, and 5, and then put dots for however many times those numbers occur. This is what it looks like. 4 zeros, you just a bunch of 2s, 1, 5, you get the idea. Of course, with any diagram like a dot plot or a stem plot or a histogram, important to label the axes. Let me go back to histograms real quick to emphasize that. Every time I show you a histogram or any graph, the axes must be labeled. On the final, on each of the instructor exams, on anything that you hand in, if you don't put on axes, labels on your axes, you're going to be in big stinking trouble. The shape of the distributions. There are a bunch of different shapes that you need to know for this class. The most important shape, I would say, is this bell-shaped curve. Symmetric, unimodal, uni meaning one, modal meaning concentration. So there's one concentration here. It's only gathering here in the middle, and it's tailing off to both sides. Whereas with skewed right, Skew is a word that means tail. So if you're skewed right, that means that there is a tail to the right. This is called non-symmetrical or bimodal. Bimodal means there's two concentrations of data. Here there's one at 7 and one at 2. It's bimodal, meaning that there's not just one mode unimodal, it's bimodal. This is uniform. I dare you to guess why it's uniform. That's right, because it's just straight across. Skewed left, again, skew means tail, so this is a tail to the left. That's what it looks like here. And then symmetric bimodal, these two gatherings of data look like they're the same size rather than these two, which look different. So this is non-symmetric and this is symmetric. Moving on to the next page here. Another data display is a box plot. You know box plots from seeing these in your math classes previously. A box plot shows the distribution of numerical data by displaying quartiles. You remember quartiles from using your calculator. And if you don't remember how to find them, I'll show you real quick. Here's my calculator. I have put some numbers into my stat edit menu. Here's stat edit. I put some numbers in here. Now, what I like to do in order to get the quartiles is go to stat and then calc and then 1var stats. It asks you if you're sure you want to do that. You say yes. And then it gives you a bunch of information, the average or x bar. It gives you standard deviation. It gives you n, which is the sample size. And then down below, it gives you the minimum, quartile 1, median, quartile 3, and maximum. These are known as the 5-number summary, otherwise known as how you put together a box plot. There you go. So a box plot is organized by writing down the minimum, the lower quartile, the median, the upper quartile, and the maximum. Please make sure when you're making a box plot, you draw the line first. You draw a number line first, and then you mark off the numbers second, because you don't want to draw a box and whisker that isn't proportional. Also, the space between quartile 1 and quartile 3, the interquartile range, that's just quartile 3 minus quartile 1. So these are vocabulary words that you need to know, and the discussion questions you don't need to know. All right, quartiles. As I said, they divide the data set into fourths, or 4 equal parts. The first quartile, quartile 1, is the bottom 25%. And then the second quartile is also known as the median. It's the halfway point. The third quartile is the bottom 75%, so that's all of these guys. And then the maximum, the largest data value, is 100% of the data lies below it. You can think of a box and whisker diagram with their quartiles as a football game. This is the first quarter, the second quarter, the third quarter, and the final score, or the maximum data value. How to find the quartiles, I showed you how to do it on the calculator. Here's how to do it by hand if you prefer, which I don't. In the example, I will allow you to do that in class. It's a fairly easy thing to do. All right, let's take a look at interpreting quartiles. This tells us that the median is 32.5, quartile 1 is 28, and quartile 3 is 38. Here are the interpretations. The 32.5 is the median, which means half of the data lies above 32.5, half of the data lies below 32.5. Quartile 1 being 28, that means 25% of the data lies below it, 75% of the data lies above it. So just to hammer this point home here, I know that 50% of the data lies below 32.5, 50% of the data lies above 32.5. I also know that 25% of the data lies below 28 because 28 is the first quartile, so this is 25%. And I know that 75% of the data lies above 28. That's why this is 75% of the data. And similarly, I could find that 25% of the data lies above 38, but 75% of the data lies below 38. Okay, that's how to interpret quartiles. Moving on to the IQR, the interquartile range. We call that the middle 50% of the observations in a data set. It's easy to find. You find quartile 3, you find quartile 1 using ye old calculator like this guy. And then you subtract quartile 3 and quartile 1. In other words, quartile 1 from quartile 3. Easy formula to remember. That's the range of the interquartiles. Here's an example, which we will do in class. And then in order to test for outliers, I know that many students come in thinking that outliers are easy to spot. You just say, oh, that one is far away. However, an outlier needs to be tested for. And the easiest test for outliers is called the fence method. Fence method is this. We calculate a upper fence and a lower fence. So here is all the data that's lined up in a row, we calculate an upper fence and a lower fence for that data. If there's any values that are below the lower fence or higher than the upper fence, this piece of data is called an outlier, and we say, we just say it's an outlier. We don't include it on the box and whisker diagram. We cut it out, we eliminate it. Anytime a data value is less than the lower fence or greater than the upper fence, it's considered an outlier. How do we find out the lower fence and the upper fence? Use the formula. Quartile 1, whatever that number is, minus 1.5 times IQR, whatever that number happens to be, right? Plug it in, chug it out. Here's an example which we'll do in class, and I don't want to do that right now with you, so that means we have reached the end of the lecture. Again, this was the Week 2 lecture on organizing, summarizing, and displaying data. Good luck studying.